This is Math 30-1, where we are starting into Chapter 2, looking at radical functions, and then in future sections, we will be looking at rational functions. As we look at radical functions here, you can see the measures of success. Given the graph of a function, y equals f of x, we want to be able to sketch the graph of y equals the square root of f of x without using technology. Or giving the graph or an equation, we want to be able to explain why it is or is not a radical function. So we want to be able to recognize it. And then we want to be able to solve radical equations by graphing, which is a little easier than in Math 20-1, where you solved algebraically. Well, here you see some warm-up questions. And as we look at the warm-up questions, we are given this function in number 1. And for this function, we are given some x values. We want to figure out the y values. So this is warm up, but let me just get you started with it. If my x value is a -1 and I was to plug it into this function here, then -1 times 0.25 will give me -0.25. In our next table, we want to know what's the square root of that function value. Well, I can't square root a negative, so here I'm going to have to say that the square root of the function is undefined. Next number in the table is a 0. If x is 0, then 0.25 times 0 is 0. And the square root of 0 is 0. A quarter times 1 is 1/4. And I'll write it as a fraction there because when I square root it, I'm going to get 1/2. Now, quick comment here. Notice that my radical has this invisible plus sign in front. So I'm only looking at the positive or the principal root. Once we have both tables complete, I'll ask you to plot the points on the grid to the right and then sketch the graph. Notice the function we're given will be a line. The radical function, you should not be using a ruler. You should be using a smooth curve. It'll have a sideways parabola type shape to it, or half of a parabola. So at this point, I'll have you pause the video. Once you finish the 3 sets of questions on this page, turn to the next page and do questions 4, 5, and 6, where you're asked to observe some patterns in what you've done in this question. So pause the video now, restart once you've finished those 6 questions. Well, here you see my table complete for question number 1, and I've sketched the graph of the line. Now I want to sketch the graph of the curve. So the square root of f of x is not defined for negative values, but it starts here where my x is 0, where my y is also 0. And then when my x value is 1, my y value will be 1/2, so my graph will go through that point. And then when my x value is 4, my y value is 1, so it'll go through that point. So here I sketch my graph. It looks kind of like this. Bit of an unpleasant looking squiggle there, so let me redraw that. If I can get a little better as I go to the right. And there we go. As I mentioned, it is half of a sideways parabola. So here close to the x-axis, we do want, I should say the y-axis, at that point, we do want to make sure that our graph starts by going straight up and then curves to the right as we go. Let's have a look at number 2. So again, our graph is undefined when x values are negative. So it starts here at 0, 0, and then at 1/2 or at 1/2. When my x value is 1, I should say my x value is 2, my y value is 1. And then when x is 4, y is the square root of 2, which maybe you worked out as a decimal value. It's about 1.4, so it's a little bit less than 1/2. So it's going to be up there somewhere. And then as I sketch my graph, this is what it'll look like. Looking at the next function. Again, my graph begins at 0, 0. The two graphs intersect at 1, 1. And then at 4 comma 2, that's where my red graph will go. My red graph is going to be above the blue graph initially, and then it's going to go below it as we head over to the right, intersecting at that point 1, 1. Let's look at the next questions. Number 4, for what values of y is the graph of the square root above the graph of the original function? Well, as I look at all three of these, we're asking about values of y. Whenever I have a y value that is in this region here between 0 and 1, my red graph is above the blue graph. Here as well, you'll see for y values between 0 and 1, the red graph is above the blue graph. And here where y values are between 0 and 1, the red graph is above the blue graph. When are they equal to each other? And again, we're looking at what are the y values when they're equal, the two graphs intersect with each other. Well, they intersect when my y value is 0 and when my y value is 1. When y is 0, when y is 1. When y is 0, and when y is 1. Question number 6. For what y values is the square root function undefined? And there, as we look back at our graph, we can see that whenever we had negative y values here, I didn't get a red graph. So on my original, if I was below the x-axis, so negative y values, I wasn't able to sketch the square root of the function. Well, all that information we can summarize here in these bullet points. First point, my square root of a function is undefined whenever my original function is less than 0. So whenever that function had a y value less than 0, its square root was undefined. And that would be when the original function was below the x-axis. Next, the squared function is equal to the original function wherever the original function was equal to 0 or was equal to 1. And we call these invariant points. So invariant points are points that don't move when we take the square root of the original function. Next, when our square root function, well, it's going to be greater than the original function. And we said that happens whenever our original function, the y values, were less than 1 and greater than 0. So again, as we look up here, whenever I had y values on my original function that were between 0 and 1, my red graph ended up being above the blue graph. So the square root of the function was above the original function. Well, why does that happen? Well, let's look back at some of the values we had here. So here when my y value is a quarter, the square root of a quarter is a half. 1/2 is greater than a quarter. So whenever we have a y value between 0 and 1, when we square root it, we get a larger number, which results in the graph being above the original function. And then finally here, the square root function is below the original function whenever our original function gave us y values that were greater than 1. Well, let's look at what this will result in as we look at these next 3 examples. What we're asked to do for these 3 questions is sketch the graph of the square root function if we know that the graph we're given is the original function, and we want to state the domain and range of both. Well, let's begin by stating the domain and range of both. And so let's look at our original function here, and we'll do The domain for this original function, these solid dots tell me that the graph begins at -2 and continues to +2, including those endpoints. So here I'm using interval notation. And again, that's the same thing as if I were to write -2 is less than x, which is less than +2, less than or equal to, because it can equal those values. I'm not going to keep the inequality version. I'm going to just keep the interval notation for the domain. Well, I would like you to write what is the domain for these next two for questions 8 and question 9. Once you've done those domains, then I'll have you restart the video. So you can pause the video at this point. Well, here you can see my domains. For number 2, because we have the arrows going down and to the left forever, down and to the right forever, we would say that the domain is from -infinity to +infinity. Remember, domain is x values. And infinity is not a number. Infinity is an idea that is just always further. So we can never actually reach it, and so we use the rounded brackets. And then for question number 9, the left end we have the dot where x is -4, so we have the closed interval on the left side. On the right side we have the arrow, so it continues on forever to the right, so we're approaching +infinity. Now let's look at the range for each of these. My smallest y value is a -1, and my largest is a +1, and it reaches those points. For number 8, my graph goes down forever. So my minimum, there is none. It's approaching -infinity, but there is a maximum of 2, and so I'll have the closed bracket on the right side. And then for question number 9, on the left side, my graph doesn't go below 0, but on the right side, it goes down forever. So it will be from -infinity up to a y value of 4, and it reaches that y value of 4. Well, now let's have a look at what the square root of each of these functions will look like. Looking back at the information we wrote up here, what I'd recommend is that we start with these invariant points. Invariant points happen whenever the function value, remember these are y values, whenever we have a y value of 0 or a y value of 1, the square root of our original function will intersect with our original. So here, y is 0, y is 0, y is 1, those are invariant points. Then, whenever our y value for our original function is between 0 and 1, our square root function will be above the original. So our graph is going to curve up like this, and it's going to curve like that. Our graph needs to be above the original function because the original function had y values that were between 0 and 1. Now as we write the domain and range for the radical function, the domain, now I see my smallest x value is a -1, my largest x value is a +1, and we reach those points. My range, my y values reach 0, but then they reach a maximum of +1. So that would be the domain and range for this original, or for the radical function. For question number 8, let me do something just a little bit different. Since I have key things happening where my y values are 0 and 1, I'm just going to put a dotted line across here where y is equal to 0 and across there where y is equal to 1. And I'm using a dotted line because it's not part of the graph. It's just a guide to give me some useful information. Invariant points happen where my y values on my original function were equal to 0, and where the y values of the original function were equal to 1. So those points will be locations where my two functions will intersect with each other. Next, it'll be helpful for us to think about that maximum value. So here I have a maximum y value of 2. Square root of 2, well, it's not a very nice number. It's about 1.4 something. So a little bit less than 1.5. So I'm going to plot a point there just to approximate. And that's a reminder that above that y value of 1, my square root function will be below the original function. And where I have y values between 0 and 1, my square root function will be above the original. So here I sketch above the original. I sketch above, and then it intersects here and then goes below. That doesn't look great. So I'm going to redraw that right-hand side as I tilt my screen a little bit. There we go. So again, each of these, since it's the square root of a linear function, is part of a sideways parabola. So it's going to start by curving up and then continue that curve as far as we need to. This middle point here, notice it doesn't look like it comes to a smooth curve, but kind of comes to a bit of a point. And that's correct because my original function came to a bit of a point as well. I won't be super picky with that. What will I be picky with? Well, let me make some mistakes as I do question number 9. First, let's do the domain and range for the square root of the function we were given in number 8. So our domain, the smallest x value, is a -2. What's going on? There we go. I think we're working again. The largest x value is a +2. And my graph reaches those points. For the range, my smallest value again is a 0. And my largest, well, that was the square root of 2. I can just write it exactly as the radical square root of 2. So I don't want to write a decimal approximation if I can give an exact value as a radical. Number 9. Again, I'm going to think along the x-axis where y is 0 and along this dotted line where y is equal to 1. My invariant points happen where y is 0, y is 0. And where y is 1, y is 1. And now this time as I look at this maximum value up there, that's a 4. The square root of 4 is 2. Now I have a nicer, easier point to plot. So I said I would make some mistakes here. Here is one mistake. That would be to kind of bulge out with my graph and then go like this. That's pretty extreme. This problem happens when we have a curve or an original function that goes up fairly quickly. It has a steep slope. The reason that this is a problem is because it fails the vertical line test. So you'll see that blue line that I drew there. If I can draw a vertical line and it cuts through the graph at more than one point, it means what I've drawn is not a function. But when we take the square root of a function, what we get still is a function. So I need to make sure that my graph is going to curve up. Oh, I should switch to red again. Here we go. Curve up and then go to the right, sort of like that. My graph shouldn't dip down in the middle there, so I'm going to fix this. Went a little bit too quick. Up and then like that. Well, as soon as I make the comment about the graph not bulging out to the side, then what sometimes happens is students try to make it go right along the curve. Well, is that on the curve or is it above the curve? Don't go too close to the curve. We still want to make sure that our graph starts by curving up, goes through the point, and then like this. And I will be fairly picky as I look at those points. So as I look at this, that's pretty close, little iffy. That's not bad. In between my graph, the red one that I drew is above the black, so I'd say that's acceptable. What are the domain and range of the square root function? Well, it's defined from -4 to +4. To the right of +4, my original function had an arrow at the end, so my original function is continuing down like this, but there I have negative y values. I can't square root negative y values or negative values and get a real number. So that's why I'm getting no red graph showing up there. Next, my range. Smallest value is a 0, and the largest is the square root of 4, which is 2. So you'll notice with all of these, my smallest value was a 0, which is fairly common, but it doesn't always happen. So don't automatically assume that the smallest value will be a 0. We'll see an example on the next page where that will not be the case. So at this point, I would like you to have a look at the next 5 graphs. It says examples, but I would like you to try these. Question number 12, pretty ridiculous, but a good challenge for us to think through. So I would say pause the video at this point. Given each of these functions, can you sketch the graph of the square root of the function? Once you've finished all 5 of them, or as much as you can do, then restart the video. For question number 10, you can see that I've plotted the invariant points and the maximum point. This time, because the original function is a smooth curve, my graph should be a smooth curve at that maximum. But this is a case where we can see that it's pretty hard to sketch our graph so it's above the original but not bulging out. So in these sections here, we want to make sure we're going above but not bulging out. When in doubt, hold a ruler up to there and see, do I pass the vertical line test? And as I look at my sketches, I think they're going to pass the vertical line test. What I'd recommend is at this point you compare with a neighbor to see what their graphs look like and give them some feedback if it bulges out or not. If I was with you in person, I would give you that feedback, but I'll have to find another occasion to do that. My graph continues up to the maximum from both sides. Switch colors, but oh no, it is still red. There we go. Should be more symmetric, but they're not a bad graph. In question number 11, again, we can find those invariant points, but this time, sometimes people get a little confused. Notice, in this section over here, I don't know why my graph keeps bouncing around. In this section there, my y values are between 0 and 1. So I need to sketch my graph of the square root function above the original. Don't think left, right, think above, below. So since I need to go above, then my graph needs to be going this direction. Same thing over here, my graph needs to go above, so it'll be in this direction. Then, as I look here on my original function, there I had a y value of 4, square root of 4 is 2, so I want to make use of those points where I can. It needs to be along the same vertical line. So along this, along that vertical line, I need to make sure that my point, where it's passing through a y value of 2 is along that line. So there I'll have another point. Here the graph will continue up like this. And here that noise is me spinning my laptop, and I'd encourage you to spin your page just to help you sketch a better curve like that. So again, notice my red graph is above in this interval, above in that interval, and then below as we go outside those intervals. Question number 12. Pretty crazy. But again, let's start with the invariant points. They happen where my y is 0 and my y is 0. And where my y value is 1 and 1 and 1 and 1, and actually all the way along here it's equal to 1. Now, as I look at the regions in here, there my y values on my original function are between 0 and 1, so my graph needs to go above the original black graph. What direction does it curve? Well, we don't have enough information to know. It's a bit of an up and down S-shaped curve actually, but we'll go with this. That's good enough. And then over here on the right side, this will be pretty tricky because again, I have a steep graph. If I spin my page around, I can sketch my curve so I'm going above the original function. Again, not thinking left, right, thinking above, below. Here I have a maximum value of 2. When I square root 2, I get that 1.4 again. So I'll be curving up to that point from both sides. Here on the left end, I have a y value of 4. Square root of 4 is 2, so I should be going through that point. And then my curve is going to continue off to the left. Notice to the right, over here, I'm not going to get a graph because my y values are negative. Let's continue on. For question number 13, as I look for invariant points, I don't have any y values of 0. I do have a y value of 1 here, so that will be an invariant point. And as I look at where my original function had a 4, the square root of 4 is 2, so I have a point here and a point there. My graph is going to be curving up like this, and I don't want to use a ruler because it will be a curve. As much as possible, I want to make it a smooth curve. So this is a case where if I was to look at what's the range of this function, my smallest y value is going to be a 1, but then it's going to go up infinitely. So this is one that I was referring to when we looked at the questions on the previous page, where don't assume that the minimum value for our range will always be 0. And that'll be the situation in number 14 as well. Now I don't even have any invariant points. My minimum on the original function is here at a y value of 2. If I square root 2, I get about a 1.4, so I'll approximate this point. And then I can approximate these 2 points where my original function was at a positive 4. And then I just sketch my best curve going up like this, and it doesn't look too curvy, but well, that's kind of how the graph will look for number 14. Let's go on to a definition. So we're switching gears a little bit now. We need to identify that a radical function is a function with this form where I have some function underneath the square root function. And it's only defined when that function is greater than or equal to 0. All right, now let's shift gears. We want to solve this equation to the nearest tenth by graphing. In question number 15, we are asked to solve this equation by graphing, and we want the solution to the nearest tenth. So there are a couple options that we have here, and you've done this before, but let's just look at it now again. I could take this left-hand side, and I could graph this as a y1 function. And then I could look at my right-hand side, and I could graph this as a y2 function. And then I would look at finding the intersection point. And what I want is the x-coordinate of that intersection point. So here, you got a glimpse of it earlier on this graph. So here, as you look at this graph, you can see that I've graphed, there's my y1, the left side, there's my y2, the right side, and when I look at the intersection point, here's what I get. My x-coordinate is 12.2. So my solution here that I get for this question is my x value is approximately equal to 12.2, and that's to the nearest tenth. So there's my solution. Well, that's not the only way to do it. What I could have done instead is collected all the terms to one side. So I could have, let's say, taken this x minus 6 and subtracted it over on the left. Well, here's what that would look like. I would get a graph that looks like this, where I have my function that was on the left side, my radical function. And then on the right side, I had the x minus 6, and now I'm subtracting the two functions. The result that I get is an x-intercept. So I'm looking to see where is this equation equal to 0. Since I've taken one side to the other, I've rearranged the equation. One side is still 0, and I get the exact same x value. So you'll notice as you look at the two graphs here, I have the same x value for both. My y values are different, but I don't care about the y value because in my equation, there was no y value. I only have x's in my equation. So two ways we could graph to find the solution for this equation. Well, you see two more questions to ponder and discuss. So I'll have you pause the video at this point and think through question 16, maybe discuss it with a neighbor, and also number 17. When you've done them both, then restart the video, please. For number 16, you see my answer there. No, it is not true for a cube root of a function because we can cube root a negative number. For example, we can do the cube root of, that's not a cute root, a cube root of negative 27, which gives us a negative 3, because negative 3 times negative 3 times negative 3 gives us negative 27. How about number 17? Well, why do these 2 points lie on the graph of the original function? And it looks like we're missing a y here. Should be a y equals f of x. Why do they also lie on the graph of y equals the square root of f of x? Well, as we look at an ordered pair, whenever I look at an ordered pair, I'll have an x-coordinate, but then my y value is the f of x value. So as I look at 0 here, if I'm doing the square root of 0, square root of 0, it's still equal to 0. So if I have the point a comma f of a, and my original point was actually a comma 0, when I look at a comma square root of 0, I get exactly the same point. And similarly here for this point, maybe I'll switch colors, we'll go to green. If I have, I'll write down here b comma 1. Because y is the square root of the function, what I'm looking at is this point. What happens if I do b times the square root of 1? And that still gives me not b times the square root of 1, but b is the x-coordinate. Square root of 1 is still 1, and so I have exactly the same point showing up on both graphs. And that's why we say they are invariant points. Well, here you can see an assignment at the bottom of the page. You can stop the video at this point, work on those practice questions, and then we'll continue on with the rest of Chapter 2 in a future video.